Okay, welcome back, and it's my pleasure to announce about Rassouli. Thank you for having me from London, who will tell us, what is the title?
It's a topological evolution of time in unimodular gravity.
Okay, you heard it. Sorry about that.
So, I will start straight in. I will say as well, I will first speak about helicity. Then I will speak about GR alla NO Tetherbone, unimodular gravity. These are the main two ingredients. And then my paper done with Jaume Reggio and Alta Etkin at Imperial. So it is very related to the Chen-Simon. Actually, it's the same. I will give an historical perspective for who doesn't know the hydrodynamic part. Helicity is the hydrodynamic part. It's not the particle helicity. Very important. Very important. So Moffat in 1968 brought helicity in this form. So U is the velocity, we are in hydro, and W is just curl of U, is the vorticity. And this is done, as I said, in 1968. It's called helicity by Moffat, and stick with it. The name in hydro is helicity. This is called topological hydrodynamics.
And the volume.
Sorry?
V is the volume.
The volume. It's the 3 volume. By the way, feel free to stop me anytime that you don't understand. I want to be the most clear possible, and we're going to use, it's going to be everything you want. It's going to be very electrodynamics in GR, no quantization at all. So very simple stuff. So this is called helicity, and I will give you a specific example just to have a feel of it. So if you have an uplink, this is an uplink, and the uplink here, it's very important. You have your space, and the uplink is made about the vorticity field. So in all the space you don't have any vorticity beside the 2 lines linked. Very important. And the helicity, exactly, it's defined as alpha ij, that I will tell you what is, F1 phi2. So this quantity exactly computes this. This is the linking number, so it's +1 or -1 on the convention. And these are the fluxes. This is piercing this surface with a flux. Phi 1 for W1. Very simple stuff. So you can exactly compute it. Perfect. These are invariants. These are topological invariants in hydro. What means that this after time, T, it can change shape, but it always will keep the linking number. Very important. In our case, they're not going to be invariants. We want to see the topological evolution of these knots. Perfect. And I will give you all the names available in literature, more or less, because they go for many names. Before Moffat, in magnetohydrodynamics, we have Volger in 1958 describing the same quantity with electrodynamics. A dot B. You can already see here is the Chen-Simon for the billion case. A wedge the A for U1. And here basically it's very easy to see that the gauge potential is your velocity field and your magnetic field is the vorticity. Because the magnetic field obviously is the curl of A. Super simple. It's also an invariant. It was discussed by Volger as an invariant in 1958. And obviously these are topological. There is no metric involved, and it's very straightforward, honestly. Another thing is very important. They're known as well as options in condensed matters. And after these two guys, there is Cassin and Arnold that basically exploited this area, and they will actually call it, instead of helicity, as Hopf invariant. Invariant. The Hopf invariant. I will give you how they give their definition, but we are speaking the same stuff. They are the same stuff, more or less. Yes. So this is more mathematical, is a pairing, and with the pairing I mean exactly the integral for a volume, again, of the pair of these curl minus 1 in dv, where I define the curl minus 1 to be A, where curl of A is. I forgot here, div of the velocity field is 0. It's very important because this defines the vector potential. The vector potential is our gauge potential. Very important definitions here, fundamental. Again, it's an invariant, it's called Hopf invariant, it's called the helicity, it's called the Chern-Simons, different areas, but they're exactly the same. It's very important, they're looking to the linkage, they're detecting the linkage, but not the crossing, basically. So for a trefoil, what a beautiful trefoil. The trefoil basically is not detected by the helicity. It's 0. If this is the only field W field that you have in helicity, or B field, this can be B field, basically is not detected. So it's detecting only the linkage. So if I put here a link of a knot, then yes, it will give you exactly what I wrote before that I cancelled. But it will give you the linking number multiplied by the fluxes. Very easy. Now we turn to gravity. GR. Unimodular gravity. Unimodular gravity, it's basically putting the Jacobian to be equal 1. It's done by Einstein in the 50s. It was for reducing the diffeomorphism, for simpler calculations, and means that the root of my energy is equal to 1. So your top form is d for x now. So you don't have the root of energy here. And we'll write you the action for unimodular gravity. So the Einstein-Hilbert. By the way, do you have any questions on the helicity part? No? No? Alright. Then we can focus on GR. So, this is the So it's very easy to see here, lambda is the cosmological constant, and it's very easy to see if you vary this action on shell, you have this equation. That is the unimodular constraint. This is basically reducing the diffeomorphism, very fundamental, of the manifold, and you can see it as a volume-preserving diffeomorphism as fluids. They have it in the Eulerian case. So the problem is that exactly this is basically restricting here diffeomorphism, but annotatable in the 80s they come up with this. So I will write the action for HD for annotated bone action. impose the unimodular constraint on shell. So you take the variation of this action on lambda. Oops. You will get exactly the unimodular constraint, UG constraint. But here we want to reopen the diffeomorphism. This is restricting the diffeomorphism, then annotated bond come up with this new action. This is a vector density, and this reopens the diffeomorphism on shell. So you will get on shell the equation of root of minus g is equal of partial mu v mu. This is very fundamental. So it's reopening the diffeomorphism in the action. Now the cosmological constant is a function, but on shell the cosmological constant is basically a constant because of the equation of motion. If you do the equation of motion and plus the equation of motion gr, nothing different, super trivial. And so now is we restore the full diffeomorphism back, and we're going to discuss this equation of motion, which is fundamental for annotated bond. And for our picture, this equation, if you integrate both sides and do some algebraic computation, you will find that the four volume basically is defined as for x minus g. There we go. So it's literally computing this in ADM. So we are foliating the 4D space in hypersurfaces. This is a hypersurface at TF, this is a hypersurface in TI. I will give you a picture. So the picture is this. So you have a volume between two coordinate time. It's equal to the computation of this V0 into hypersurfaces. So basically, here you have hypersurface of Ti, T initial, hypersurface of T final. Very easy. These are computation. So when I write these basically hypersurfaces, I mean literally the integral of V0. So you're computing is a number. Here is a number. By the way, the helicity is fundamental helicity and abelian Chern-Simons is a pseudo-scalar. It will give you a number. Important. So basically, annotated bond, what they've done, they redefined this as the physical time. Which we define as delta t. This is a physical time for the Hamiltonian analysis. You can do an Hamiltonian analysis, is the conjugate of the lambda and is the physical time. It's not the coordinate time. You have here a coordinate time, little t, but it's not that. It's a physical time. It's giving you how it evolves. Yeah. I think we have enough information right now to go to.
What do you mean by physical time? Like the time for an observer at if or?
No, it's given by exactly the Hamiltonian analysis. In ADM, basically you will have a physical time evolving. If you do it's a conjugate basically. You do an Hamiltonian analysis, so this is a Lagrangian. You will change it to an Hamiltonian, and you will find exactly. Yeah. It's the physical time. I'm not proving to you, but it's in the paper of annotated bond. And what about knots? What is happening here? Where are the knots? Where is the topological evolution of time? We're getting there. So now we have both of background checked. Very easy. we can see here some peculiarities. So, this is the annotatable action. 2 seconds. We are working with this theory. And the annotatable action has, as I said, has this component which is lambda partial mu vector density p for x. Is it similar to something in 4D? What is similar? I will give you the answer. We can put it as f wedge f, the chain-point triangle. And we can easily see why it's the same, because in form notation you can pull out d and you have a wedge d inside. Right? Yes. So the main step here is annotatable. For general partial mu v mu, we put chain-point triangle. So we put a U1 gauge field. Super easy. And let's write it up to science, guys. You can stop me if you don't understand something. So this is without the DG, let's say, writings, and this is your V mu. Mu are contracted, that's V mu, and is a density, fundamental. I will define as well F tilde for completeness. It's just, the Hodge. There we go.
Where did you fix the gamma mu?
Gamma mu? Sorry?
Gamma tilde mu, right? The leftmost del mu, gamma tilde mu. How did you write it as FHF?
Gamma? V? No, basically this is contracted, this is our V mu.
Okay.
Because, what's this? And it checks everything. This is a 4 form. We are in 4D. Very important, we are in 4D as well. And yeah, you can do it. I think Wickman did this already. This is you can see it. Okay, I will give you another references. You can see this as axionic. This looks like an axionic situation here that is happening. And they use this in electroweak phase transitional universe, for example. Or early cosmology, basically. Early universe cosmology. Okay. So, where the knots arises, so we have this equation of motion, fundamental. We need to calculate our physical time. Let's calculate our physical time if we put f wedge f instead of partial mu v mu. So our physical time, t lambda t for a given coordinate time is on the hypersurface t d. By the way, this I mean the coordinate on the hypersurface. D0. Let's compute it directly. I will show you d3x. So here, basically, exactly, I'm completely opening, there is a 0, I'm taking the 0 here, and the 0 is fixing from 4 dimension, we go into 3 dimension. This is when we go to 3D. We fix to the hypersurface, very fundamental. And you can see exactly that, what is this? This is basically minus ijk partial j ak. This is nothing more with a d3x here. This is the Chern-Simon. In our case, it's the Chern-Simon, or the helicity, in the fluid case. Here. Fundamental. So, the forward volume in this case is given by delta t, we said. Now is delta h, up to minus delta h. So, what is computing exactly is if you have a link of these B fields and then they become unlinked, you have an evolution of time. If the off link still remains off link, this is 0. Very fundamental. Do you have any questions? So basically, if the B field evolves in time, coordinate time, then you can have basically the physical time evolving. Physical time cares only on the change of the B field topologically with linked manner. This is very different from Witten perspective. Witten usually see it as a particle moving, and usually these are invariants. Here we have an equation for evolution of invariants. So we're linking from 4-dimensional theory to 3-dimensional theory and looking to each hypersurfaces. And if the two hypersurfaces doesn't have the same topology, then you have an evolution. Very fundamental. You have time when B evolve topologically. And there are some other peculiarities that I will give. So, usually in fluid dynamics and in the abelian Chern-Simon, the dot of H, which is the Chern-Simon, is 0. Because you don't have an evolution, it's an invariant, okay? In our case, it's not. In our case, basically what you have is su E dot P. Integral, okay, a second, epsilon 0 su E dot P. And from the equation of motion, there is this other particularity which is very interesting. It's equal to d3x n root of minus h. H is the pullback of G on the hypersurface, is basically the metric on the hypersurface. So, not only E dot B is not 0, usually E dot B is 0, if they are orthogonal. Here in GR, the space is curved, is non-zero. And this is a very fundamental result. It means that you have a topological evolution. This is a recurrence of turbulence in hydro. I will give you the hydro version of this. In hydrodynamics, they say that this quantity, when it's not equal to 0, you have turbulence. This is vorticity, is our B. This is called the swirl vector. In our case, it's the electric field, sorry. And this is the viscosity. Looks like something is damping this scenario. So basically, looks like that you're having these knots unlinking, linking, evolving time. Or time cares about only when there is a topological evolution of the Biel field. If there is a linkage or a linkage, then you have time in 4D. And there are many others important results from this. Equation of motion in our case is root of minus G d for x equal, can you see? F wedge F, right? More or less. I will rewrite here. Up to sign. D for x. F wedge F. You can compute F wedge F. F wedge F is just up to, don't take me seriously with the signs and numbers. It's E dot B. But E dot B, what is E dot B? If you take the determinant of F, you know F is dA, by the way. F is E dot B squared, something on these lines. So this is just equal to the root of the determinant of F. What is happening? There you go with D for x. Why from the equation of motion we're getting that G and F are related? It looks a little bit, if in string theory, looks a little bit, I forgot the name. There is a theory that relates G and F, determinant F, you know. Very famous, I forgot. But it's strange. This is strange as well.
Can I have a question?
Yeah, go.
What is F? Because
F is,
I understood correctly your first, like,
Yeah.
rewriting those d mu, mu.
yeah,
It's just some kind of, A is like some kind of one form and F is a two form. That's so, but it's like an arbitrary one form, or is it like some kind of special?
electromagnetic.
Okay.
It's literally F mu, like F mu. I will tell you something else very interesting. F, if you put it down in 3 dimensions, is B.
So it's
B-
just like magnetic, like the
Yeah.
well tensor.
Yeah, okay. I will give you. So F mu from standard textbooks. So you have 0 here, you have E, right? Then you have 0 B, 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 0, 0, B. I think I'm doing something wrong here. There we go. I put an extra B.
So the physical interpretation we should have is that is literally magnetic and electric field.
Yeah, no, but you can see it. Restrict these to R3, sorry, just as an example. You kill the time part. You get B. Up to signs, guys. I'm not putting correctly signs. And X, this is an X, this is a Y, this is a Z, right? But it's very fundamental why, when you go to 3 dimension, which is the hypersurface, B is a curvature. B exactly is a curvature. It does have as well a mathematical interpretation. B is something more deeper in 3 dimension, going from 4 to 3. Fundamentally, if you start F mu, if you start with electromagnetism in 3 dimension, you don't get this B. You need to have 4D B, F, then going to 3D, B is a curvature. It's crazy. It's a beautiful, it's beautiful. So basically, B is now a curvature of the connection A. And we're looking, the theory is looking to his knotting. It's very important. Let's say you have this. So in the hypersurface, you have only knot flink. Next hypersurface, you have a knot flink. What is the volume here? It's 0. Doesn't exist. Time doesn't care if there is no topological evolution. In the moment that, I don't know, you add another thing, like it opens or reattach, or you have a topological evolution, then you have the 4 volume. And I told you as well, like it looks like that gravity is dampening the E dot B. E dot B is not equal to 0 in this theory. which looks like that there is turbulence. So this you can as well not look at you can dump it down from not being GR. This is a beautiful technique to see an evolution of invariance. The difficulty right now in plasma physics, dynamo theory, or any other important physical subject is turbulence. How we can see this evolution? How we can predict as well evolution? And this looks like a starting point to see a collection of different invariants. Right now, I'm working on putting this theory in 3 dimension and 2 dimension. The topological things changes, but in 2 dimension you can have a JT with a JT gravity situation, and you will find that your time is the holonomy, is exactly the Wilson line. For example, it's very rich, it's strange, and we didn't touch the quantum part. You can quantize it. It's not been done. This is basically the paper on. It's a simpler version of the paper that we published on December, I think, October last year with Joao Morejo and Alt Aitken. And again, it's a neat formulation of having an evolution of invariance. Yeah. You can, by the way, you can go non-abelian. What's the case in non-abelian? Basically, the helicity will calculate it's called cross helicity, and it will calculate. You have basically 3 fluids. You will calculate the linkage between these 3 fluids if they're linking as well the cross linking, for example. Yes. I think I finished. Very direct. So
Good.
very simple.
You have some questions?
You can ask any basics.
Just a stupid question.
Yeah.
Very good.
In that equation, the second f, should it be like the Hodge duality of the f?
No. Yes. F. Are you
Second
asking?
F, yes.
You're asking there is a further symmetry. F is equal to dual F. Hodge F. Yeah. We have this auto symmetry. Actually, Professor Anani told me this symmetry, and we didn't further analyze that. Yeah. There is no F squared. By the way, this is not F squared. This is a topological term. We didn't add the F squared. You don't have dynamics. You don't have dynamics of A. Looks like that GR is modifying B and E, so basically it's giving, if the space manifold is curving in different ways, E and B are basically as well following, and it will give you basically this strange evolution, topological evolution. Yeah.
But also,
Yeah, please.
so the knots are the degrees of freedom somehow of your topological degrees of freedom of your theory, and the action regulates their evolution. Understanding.
It's an equation of motion. The action, so we're looking to the equation of motion.
Yes.
We manipulate the equation of motion, and they must follow something on this. They must follow the equation of motion, right?
Also, the initial state should have some link in somewhere. Otherwise, what's
No. Let's say that there is no link here. Then you have a link. You explicitly compute the helicity. The helicity here is 0. The helicity here is the linking number multiplied by the 2 fluxes. So in this equation, one term is going to be 0, the other one is not. Make sense? You can start from 0, nothing.
So you can start from nothing, and then the dynamics will produce some.
Yes, on the paper we discussed this. We give a monotonic version of. So you have you start with a lot of links and they go on, and as well with. By the way, I didn't speak. I wanted to give a very easy intro, and you can as well fix the fluxes. The fluxes, so you can have. So if you have many links the fluxes are all the same, so you get only the linking number here, right? The linking number. And it gets step, by the way. That's another feature that I didn't discuss. It gets literally step, so it's discretized. You cannot have a continuous, it's discretized, must be discretized. We didn't discuss as well the gauge transformations and all of these, but if you have questions, well, I'm happy to reply. What is the difference between this picture and Witten? I sent an email to Witten as well that he didn't know about helicity and Opf invariant, because Witten was following, basically, he told me it was following, Polyakov paper. Polyakov paper just mentioned the Opf map. These are all related. All of this is related. Opf map, options, Opf link, all of these are related. Chern-Simon, helicity, options, Opf invariant, they're all related. But they live in different academic world. This is topological hydrodynamics, it's called.
Yeah, it's still not obvious how this evolution can lead to nothing is there, but then something gets created. It's not very visible.
No, I can give you an example, which is not physical though. So this is speculation, by the way. So what we're stating here is if in two hypersurfaces you have a different linking situation of the B field, then you have a full volume. We say that only that. But if you take your full 4D manifold to be like a T4, and you slice it, the first slice is this, the second slice is a genus 2, and then you slice it again, it will give you something with a torus, and then again sphere. These are your hypersurfaces, and these will give you the E and B's here, they will change. So you, like this is, but the problem here is the universe is finite. So it's starting a point, it's finishing a point. It's not an infinite. So basically, the curvature of GR is not making E dot P to be equal to 0. And so you have a non-trivial topology. The helicity is non-trivial. If it was flat, then yes, the helicity should be trivial. We didn't add here F squared, the dynamics. We're looking without dynamics. GR is feeding to the P field. This is the way around. This is a completely non-physical and heuristic. This is just to make understand more or less. There is a curvature, there's cycles. Really, they're non-trivial.
Any other questions?
So you cannot have like gravitational waves.
Of what?
Like, are there propagating degrees of freedom in the metric?
That's a good question. I don't know. I'm going to be honest, I don't know. But unimodular gravity, they use it there are also papers on gravitational fields. That would be a good. We didn't quantize, by the way, again.
Yeah, but even classically.
No, classical, yes. I need to speak with somebody.
Okay, so let's thank Arwold again. I'll stop the recording.